So in this question, we're asked to solve for the transfer function g, which is equal to the voltage out divided by the voltage in. So V in is pretty easy. That's the voltage provided by the supply. And in this question, the voltage out is going to be the voltage dropped across this specific capacitor. So in terms of the approach to this question, for the electrical ones, you can either use the mesh analysis or the nodal analysis. But I tend to prefer the mesh analysis, and it's especially good when you have voltage inputs to your system. If you have current inputs, then nodal becomes sometimes more appropriate. So I'm going to apply mesh analysis, and what we need to do to set this up is draw in the current in each part of our mesh. So this here is going to represent one mesh, and I'll call the current running through it I1, and this in here is going to represent a second mesh, which I will call the current in I2. So let's start with looking at this one, which I'll call mesh 1, and developing the equation that describes what's happening to the voltages inside it. So what we know is that in this mesh, the sum of the voltages have to be equal to 0. So basically any voltage gained has to be equal to the voltages dropped. So I'll call a voltage in a positive and a voltage out negative. So if I start down here in the bottom corner, when I go across this side of the circuit, I end up gaining a voltage V in. Across this bit, I'm going to drop voltage across the resistor, so it's going to be minus, and we know that voltage is equal to the current times the impedance, Z. So for a resistor, it's going to be equal to the current, so through this resistor we just have I1, multiplied by its impedance, and for a resistor, that's just its own value, so R1. Next, we're going to consider what happens when we go down here. Now again, it's going to be a drop across the component, so it's going to be minus, and it's going to be equal to the current flowing through it. Now this time, because this one's like branched across two different meshes, we're going to need to take the difference in the current. So this is going in one direction, and this is going the opposite direction back through it. So it's going to end up being the difference between them is what's going through this specific component. So it's going to be I1 minus I2. I1's going in the direction here that we're considering, positive, positive I guess, and this is going the opposite, so that's why it's been taken away. Alright, so then we need to multiply it by the impedance. And for a for an inductor, the impedance is LS. I'm just jumping straight into the plus form here. Alright, so the last one is that we're going to drop again across the resistor here. So it's going to be minus. The current going through it is just I1. It's not part of another mesh. And the impedance is R3. And that all has to be equal to 0. So what I'm going to do is try and rearrange this equation to make it nice when I have to go through and solve these equations simultaneously that I'm going to develop. So for that, I'm going to leave V in on the left-hand side, and I'm going to shift all these to the right-hand side. Sorry, this should be plus. And I might expand this at the same time. Alright, and now what I want to do is factorize out my currents. So I1, if I factorize it out, I'm going to have this one, and this one. And for I2, I think it's only in here. Alright, so I'm going to leave it like that, and we'll come back to solving it in a moment. So now what we need to do is look at what's happening for this second mesh, and I might do it up here. So again, the equation that we need to solve is that the sum of the voltages around the mesh is equal to 0. So I might start in this bottom corner again. This time I might everything's going to be a drop in this one because we have nothing coming in. So what I might do is just treat everything as positive, make it easier. So across this, we've got a drop of LS times by the current going through it. So this time I2 is going one way and I1 is going back the other way. So it's going to be minus. When we get up to here, we now drop across a resistor. So it's going to be R2 multiplied by the current going through that part, which is just I2. And then we're going to drop across the capacitor. So the impedance of a capacitor is 1 on CS, and we just have the current I2 going through it again, equals to 0. So again, you could have put all negatives on these because they were dropping, but you were just going to end up flipping them anyway. So now let's go ahead and expand out this part. And we'll factorize it. So if we take out everything that's got I1, this is the only bit. And for I2, we have a few things. We get that. So these are our two simultaneous equations that we need to go ahead and use to solve. So remember that what we're looking for is the voltage out divided by the voltage in. So I'm going to go ahead and use Cramer's rule to solve it again, which is when you put everything into a matrix. So the matrix is AX equals B. A is the matrix of coefficients in front of each of our unknowns, so I1 and I2, and X is the matrix of unknowns, and B is the matrix of what's on the other side. So let's go with this one first to fill in. So it's going to be R1 plus R3 plus LS, and for in front of I2 we have negative LS. So these were the two unknowns, and on the other side our constant is V in. So for this bottom line, it comes from the second equation. So we've got negative LS here, and we have this, and the constant on the other side is 0. So now what I just wanted to quickly mention is how we can relate back what we get inside our matrices to what we had back up in the original question. So I've just copied it down. So what we can see is on the diagonal, we've ended up with everything positive. And what you'll find is that this top one related to M1. So, sorry, not M1, mesh 1. So what you'll find is that this here is going to be the positive of everything that was included inside mesh 1. That was a component anyway. So we're going to have R1, R3, we've got both of those, and also LS. So that all got picked up in there. This one related to mesh 2. So you should pick up every component that you have in mesh 2. So we have L, which appears, we have R, which appears, and we have C, which appears. So that's good. On the other side, reflected across the diagonal, we end up with the negative of everything that's in between our meshes. So between mesh 1 and mesh 2, all that we have is the inductor, and you see that we end up with the negative of its influence in there. Finally, on the right hand side here, you end up with any voltage inputs that appear in that mesh. So V in ends up in mesh 1 here, and we had no voltage inputs in mesh 2, so that's why it didn't end up in the equation. So let me just quickly write out the pattern. Right, so this is the pattern for the pure mesh analysis stuff, or pure electrical systems. So on the diagonal, we end up with the positive of all the components within each mesh. And on the other side reflected, we end up with the negative of what's in between them. And on this other B matrix, we end up with the voltage inputs in either mesh. So these are the external ones added to the system. Alright, so now we're up to the point where we can go and solve for our transfer function, remembering that what we wanted was V out divided by V in. So we have V in appearing at the moment, but we don't actually have V out. So we need to go back and see how we can obtain it. So looking at our system, we're measuring V out as the voltage dropped across our capacitor. So what we can say is that V out is going to be equal to, alright, using this, the current running through it, which is purely I2, multiplied by the inductance. Sorry, impedance is the word, impedance. So the impedance through your capacitor is 1 on CS. So V out is equal to this, and what you'll find is if you rearrange it, I2 will be equal to V out multiplied by CS. And we're going to be able to use this in a moment to go ahead and solve for the transfer function. So because V out is directly related to I2, if I jump back down here, what I want to solve for is I2 using Cramer's rule. Okay, you can also do it with substitution, but I prefer this method. So solving for I2, it's going to be equal to the determinant. This is the second variable, so when we put this into the second column. Divided by, we need to just copy down our A matrix now. Alright, so now we can go ahead and start solving for the determinants, but what I'm going to do is, rather than solving for I2 directly, we can substitute in that we know I2 is directly related to V out through that relationship. So let's sub that in. So V out, CS, got subbed in. So on the top line, the determinant here is going to be this times this, which is 0, minus this times this, which is V in LS. And now we just need the determinant that comes from the bottom line here. And we minus away this. And since they're the same, I'm just going to square it. So we're looking for V out divided by V in, and we can get that now. So we have V out here. If we divide by V in, we got our transfer function, and this will obviously then have to get taken away to the other side as well. So we're going to end up with LS divided by CS. Let's just put it on the top line though to make it a bit nicer. So this is getting divided. And then this all needs to be expanded out. So let me go ahead and do that. It will be a bit lengthy. So that's all of this bracket expanded out, and this one on the end becomes L squared S squared. So for these pure 2 degree of freedom systems that are only electrical, what we should find is that whatever falls out in the negative part of the determinant here cancels with something else in the equation. So this is going to end up cancelling with this. And what we can do is get our final kind of answer. So I can cancel out those S's as well. So I'm going to get L on C, and I'm going to go through and try and factorize out the different components that I have. So in terms of the S components, I've ended up with this one. I've got an LR2 as well, and an LR3. For the constants on their own, I've ended up with R1, R2, ended up with an L on C and an R3, R2. And I've also ended up with a couple that are divided by S. Let me put 1 on S out there. So usually what you would want though is for your transfer function to just have powers of S starting from a constant and increasing. At the moment this is like S to the -1. So if we want to fix that and make it look a bit nicer, If we multiply top and bottom lines by S, we're going to end up with L on CS. And all the bottom line powers of S's are just going to be increased by 1 from this one here. So let me just copy it out. Oops. So these are going to cancel, and that just becomes a constant on its own. So that's our final answer for relating together the voltage out across the capacitor to the voltage in provided by the supply. So that's all there is, and see you in another video.